Okay, what is work, energy, and power? Well, look, you probably have some understanding of what energy is, and probably some understanding of what power is. Work might be a new term for you. Oh gosh, I didn't mean it like that. I meant in terms of physics, not you're lazy.
In terms of physics, she's not wrong though.
All right, so you might not know what the term work means in a physics sense. That's great. Okay. It sure is. It is force times displacement. Work is done when a force causes an object to undergo displacement. So if there is no displacement achieved, then no work is done. For example, I might push on this bench top and I am applying a force to it. I can feel that. I don't know why I'm pushing quite so hard. But it's not moving, so I haven't done any work. Okay? No work has been achieved. Okay? But force has been applied, but no work because it's not moved. Whereas if I do the same thing to this pen, work has been achieved. Do you understand? What? Did you say rabbit? Okay. Rabbit. How much work is done by a force of 35 newtons east that moves an object 12 meters east?
A lot.
Well, no, well, a lot is relative anyway. So W equals Fs is our formula, yeah? Okay. So we're going to go 35 times 12. Are you dissing me? Because I always say that. 420. Okay, what are the units for work? Joules. Does it say that here? Yes. Oh yeah, joules. $420 Okay. Now, what about a direction? No, tricked you. Who said doesn't have one? Oh, that's very good. Good job, Jacob. Yes, there is no direction. How fun. It's scalar. Work is sort of like energy. It is energy. It's the change in energy. Okay? And energy does not have a direction. Which kind of makes sense, don't you think? Energy wouldn't have a direction? If you think about your energy. No? I mean, if you like convert some electrical energy to light energy by plugging a light in, you know, you talk about how many joules that has. You don't give it a direction, do you?
No.
Thank you. That's what I needed. Yes, thank you, Mohammed. Okay, this one here. A motor which lifts a 100-kilogram load through 15 meters at a steady speed. So we've got the displacement there, 15 meters. But to find the work, we need to find the force. So we need to calculate the force that the motor applies to the load. Okay? So we're back to thinking about forces, which is fun. Here's my load. Here's my motor. Oh gosh, this is so silly. All right, steady speed. What is the net force?
0.
Yes. So the net force is 0 because the acceleration is 0, okay? What forces do I have acting on my load? Gravity. What is the force that opposes gravity?
Tension.
Yep, tension, which is the force of the motor, right? Okay, so my tension force is the force of the motor, and that is the force that we want to find because we want to know how much work the motor does. So we need to find the force that the motor applies. Does that make sense? And that's going to be equal to the force due to gravity because the net force is 0. Yeah? And which one of those am I able to calculate? Force due to gravity. So let's do that. So the force due to gravity is the mass times gravity, which is 100 times 9.81, and I can do that one in my head. I know. Ew. 981 newtons down. Not that really matters. So therefore, the force due to tension must be 981 newtons up. Make sense? Okay, so now that I have the force exerted by the motor and I have the displacement achieved, I can calculate the work. The work is the force exerted times by the displacement, which is 981 times 15. Can't do that one in my head. 100, wait, no, sorry, not 100, 14,715, what? Joules. In what direction? No direction. Good. Lovely work, everybody. Now that we have done that, let's do some problems from the blue physics book. I want you to do questions 1 through 5. I want you to cross out question 6 and question 7. Because they're not in the course. You can do them if you want to for fun. Okay, energy. What is the relationship between energy and work? Well, yes, you need energy to do work. Oh, stop that. And work is equal to change in energy. That's very important. Work is equal to the change in energy. Okay. Now there are 2 different types of energy that we look at in this course. There are many different types of energy in the world. But in this course, we primarily look at 2, which doesn't mean that you don't need to know about the other ones at all. But the ones that we do calculations for are potential energy and kinetic energy. Have you heard of those?
Yes.
Okay, so you gain potential energy by gaining height. The further above the ground you are, the more potential energy you have, because you could jump and convert all that energy to kinetic energy, okay? So you've got potential energy with that height. Kinetic energy, do you know what that is? Yes, energy of movement, okay? Energy and movement. So potential energy is all about height, and kinetic energy is all about velocity, effectively. Okay? All right. What other types of energy do we know about?
There's a big list.
There's a big list. Let's look at them. Okay, gravitational potential, that's the potential energy that I just talked about. Specifically, it's called gravitational potential because there's 3 different types of potential energy. Okay, which is energy that's there to be used and hasn't been used yet, I suppose. We've talked about kinetic energy. Another type of potential energy is elastic potential. Now, we don't need to know any calculations about elastic potential energy, but you can still get questions about conversions of different energy. So I might say, if I flick a rubber band to you, what energy conversions are going on there? So rubber bands are elastic. You stretch it. When you stretch it, you're giving it elastic potential energy. You let it go. What's that converted to? Kinetic. Unless you fire it upwards, in which case it's converted to kinetic and then potential. Anyway. Heat. Heat is often wasted energy. I mean, not always. I mean, we like heat, but a lot of the time, the things we do or the energy we use, heat is a byproduct and gets wasted. So, for example, where might heat be a wasted energy? Does anyone have an example? Yes. What did you say? I don't know. Like, I mean, sure. Yep. Yes. Or a light bulb, right? If we have a light bulb, generally what do we want to get out of our light bulbs? What type of energy? Light, right? But light bulbs can give off some heat, and that is wasted energy. So the electric energy that goes in, some of it is given off as light energy, which is great. Some of it wasted as heat energy, which is why we try and, with our new light systems these days, we try and make them not give off heat as much as we can. Anyway, nuclear energy, don't know much about that. I mean, I guess it's, like fission reactions and stuff. Remember that?
Yeah.
The energy that's given off as a result of fission. What else? Light, we talked about that. Electromagnetic radiation, really don't know much about that one. Let's skip that one. Sound. I am right now converting my energy to sound. What energy do you think I'm converting to sound? No, I'm not nuclear. Who said that? Brody? Chemical energy, yes. We as humans generally convert chemical energy into other forms of energy for us to be able to do things, like if we dance or just move in general. Then we're converting our chemical to kinetic, aren't we? Yeah? Okie doke. Electrical, obviously, that's electricity. Well, sort of. Electrical energy. Okay, so if we plug something into the power socket, we're converting electrical energy into whatever we want to get out of that thing. So if it's a heater, heat. If it's a light, whatever. Yeah? Fantastic. Those are some types of energy. So the types of questions that you can get are, what conversions of energy are occurring in this scenario? So you have to figure out what the conversions are. Do you understand? Those questions don't come up much. All right. The first type of energy that we're going to look at is gravitational potential. And the formula for potential energy is the mass times gravity times the height. So it's not a very nasty formula. The mass of the object times by 9.81 times by how high above the ground it is. Yeah? Oh, we're also doing kinetic energy at the same time. It's okay. It's all right. We don't have to worry about all of this, just this bit down here. Don't worry. This is how it's derived. So where the formula came from, which is not in the course. If you're interested in where the formula comes from, have a read of that, but you don't need to. What you do need to know is the formula, but you don't even need to memorize it because it's on the formula sheet. How good. So kinetic energy, to find kinetic energy, we do half times the mass of the object times by the object's velocity squared, and that's its kinetic energy. Not so crazy, is it? Not so scary? Mechanical energy. Mechanical energy is potential energy plus kinetic energy. Okay? So mechanical energy. Is this not in there? Can you add it? Just what I've written here in red. No. So mechanical energy is potential energy plus kinetic energy. Now, in a perfect world, mechanical energy would be conserved, okay? So if there is no wasted energy, then our potential and kinetic energy before something happens should be the same as our potential and kinetic after that thing happens. We'll look at examples of that. They often involve roller coasters in physical sciences. Okay, we do lots of roller coaster questions. Now, can we just notice this? Air resistance. Do you have this sentence? Can you write that down too? Actually, write all that down. Find the change in potential energy when a 15 kilo mass is lifted through a height of 1.5 meters. What is the formula for potential energy? Yes. EP equals mgh. Connor? Finley? Jack? Shh. All right, mass is 15. Yes? G, everybody think about what G is. Have it in your head. What is it? What about H? Everybody think about what H is going to be. Is that right? Rounded to 3 sig figs? 221 joules. Okay? Is the potential energy that's achieved. So when it was on the ground, how much energy did it have? Potential energy. None. Yes? And then when it was finished, being lifted, it had 221 joules. So the change in potential energy started off at 0. It ended up at 221. So it's 221 joules, isn't it? Is that okay? Shall we do the next problem now?
Kinetic energy have direction?
No, and no energy has direction. Good question. All right. So let's find the kinetic energy of this cyclist. So what do I need to do? I need the kinetic energy formula, yes? Half mv squared. So substituting in, what's m? 100. What's v? 22, and we square that. Now, you just have to make sure, what are the units for mass in this course, in physics? Kilograms, make sure mass is in kilograms. What about velocity? Yep, make sure it's in meters per second. Make sure you don't have to do any converting before you start plugging it into the equation. Okay, 24,200 joules. All right, next one. Now they just want us to have a go at sig figs. I'd like you guys to maybe try this one on your calculator so that I know that you can do sig figs on your calculator. So same thing. We have its mass and its velocity, and we want to know its kinetic energy. So half mv squared. So in the calculator, we need to put half times 9.1 by 10 to the negative 31 times 2 times 10 to the 7 all squared. Now, to help from running into problems, it helps if you use this little exponential button. Now, yours might look different. It might look like 10 times 10 to the power of x or something like that. But it really helps if you use that button. It saves a lot of issues. So the way that you use it, I'm going 0.5 times. Now I'm going 9.1. You press it, and it means times 10 to the power of. So then you just have to put the power. So I've gone 9.1 exp negative 31. Okay? Times, I'm going to use brackets just in case, 2 exp 7 close brackets, squared. I don't know if the camera will be able to see that, probably not.
Calculators are bullshit. Don't even.
So you should get 1.82 by 10 to the negative 16, right? Now, we've already talked about this. Shh. We already mentioned this, right? Work is change in energy. That's the basis of what we're looking at there. Just work is change in energy. Fabulous. Let's go to the question. Okay. What? Yeah? Fab. Okay, a 200 kilogram cart moved from rest to southwards at 5 meters per second. What was its final kinetic energy? So we write EKF. Okay? Kinetic energy, final kinetic energy. Half mv squared, or mv squared, yep. And m is 200, v is 5, square that. Change in kinetic energy is final kinetic energy minus initial kinetic energy. Change in anything is always final minus initial. Okay, so the final we know is 2,500. What's its initial kinetic energy? Why is it 0? Yeah, its velocity is 0, therefore its kinetic energy is 0. So therefore the change in kinetic energy is 2,500 joules. Okay? Next. How much work was required to bring the cart to that speed? Yes, good. Work equals change in energy, which we just found, and it was 2,500 joules. Same answer 3 times in a row. Okay. If the accelerating force was 500 newtons, how far did the cart move while the force was acting on it? What formula do I use here? Did anyone get an answer then? Yes, thank you. Work equals Fs. Okay, the work we found up here, so 2,500 equals the force, which is 500, times that by the displacement. So 2,500 divided by 500 is 5, isn't it? 5 meters. Now, page 37, question 8 through to 11, please.